If you are struggling with collision in Unreal and you're asking yourself, what are all these collision settings and queries and when should I use what? Why collision is not behaving correctly? And how can I debug and fix collision issues in nearly no time? And you're wondering, what are some of the best practices I can apply to keep collision optimized and manageable in a scaling project with complex scenes and dozens of collision channels and queries? Then rest assured, I've been there too, and in this two-part video, we'll answer all of these questions. As we answer them together, we'll look at some examples that will help us get a better understanding of how collision works under the hood to remove any misunderstanding we might have on collision. Then we'll see some of the best practices we can apply when working with collision to keep it efficient and under control. And lastly, we will cover some of the tools we can use and develop to detect collision issues and protect ourselves from falling into them in the future. In this first part, our goal is to get a better understanding of how collision works by answering the main question of what can cause collision to not work properly and get out of control. In the second part, we focus on optimization and answer the question of what can cause collision to work poorly and cause performance issues. I must mention that this video is heavily inspired by this Unreal Fest talk by George Prosser, which explains that the reason behind this struggle and confusion is the misunderstanding of the many collision settings and queries in Unreal, and then shows some of the best practices and tools they have developed on Hogwarts Legacy to keep collision manageable, efficient, and easy to debug, which we'll be developing in this video. I highly recommend you watch George's talk, look at the other resources mentioned in the description below, and you can grab everything we'll be developing in both parts as well as my notes from my Patreon. A huge thank you to everyone supporting this content. And without further ado, let's get started with this part's main question. What can cause collision to not work properly and get out of control? Let's look at an example to answer our question. Here we are using a modified version of the StackObot sample in Unreal 5.4, and we gave our bot the ability to shoot projectiles. But when we shoot a projectile, we notice it passes through this wall and doesn't collide with it. A lot of things can be causing this issue, and this is what usually causes confusion. But most of the time, it really goes down to answering a couple of questions. At the moment of intersection or impact, does both intersecting objects have collision geometry? Does both objects have the right collision enabled setting? Does both objects have the right response to each other? And is our query set up correctly? Let's answer the first question. Does both objects have collision geometry? For any object to be involved in collision detection, it must have collision geometry. These are the primitive shapes like boxes or spheres of a shape component with triangles of some static or skeletal mesh component. In Unreal Engine, we have two types of collision geometry, simple and complex. And these are stored within the body setup of each primitive component once it's created. The complex geometry represents the triangles of a static or a skeletal mesh. And the simple geometry for a static mesh is any collision shape created in either a 3D software or within the editor. And for a skeletal mesh, the simple collision represents the bodies in its physics asset. The reason behind having two types of collision geometry is that sometimes we need to perform very precise queries. For example, if we wanted to shoot a bullet that passes through tight windows, or if we wanted to get the exact vertex that was hit by query. This allows collision queries to choose whether they want to be precise and detect collision against complex geometry, or to be efficient and detect collision against simple geometry. Each body setup also has the ability to use both simple and complex geometry, or to choose one type over the other. For example, if you have a tree made of thousands of triangles that represents its complex geometry, and has a box that represents its simple geometry, it can choose to override complex geometry and use simple geometry as complex. So, when a query asks us for complex geometry, collision gets checked against the single box instead of the 1,000 triangles to save some performance. But more on that in the second part of this video. If we get back to our example and take a look at our projectile class, we can see it has two primitive components, a sphere collision component and a static mesh component. To visualize their collision geometry, we have a couple of ways. We can use the console command showFlaggedCollision, which is similar to the show setting in the viewport. But this could be misleading, since we need to visualize the geometry at the moment of intersection, as something might change it at runtime. And it's also hard to understand what's going on in our case because our projectile is moving quickly, and we're not sure whether the two shapes are intersecting or not in the first place. So, a better way to visualize collision geometry is to use Case Visual Debugger. I will not get into the details of how to use it in this video, but you can find its documentation in the description below. We can open it from debugging tools and record our issue. Then, if we take a look at the recorded session and ensure we enabled viewing collision geometry, and then moved our timeline to the moment of intersection, we can see the complex and simple collision geometry of both our wall and projectile. So, now we are sure geometry isn't the issue, since both objects have collision geometry at the moment of intersection, and this geometry is scaled correctly, and they are indeed intersecting. Let's start answering the second question. Does both intersecting objects have the right collision enable setting? Besides collision geometry, one important thing about the setup stores is a body instance. This is the structure that we are very familiar with its details panel, yet most of the time we are confused about it. It groups a couple of settings used for collision detection in a named group we know as a collision preset. For now, let's focus on the first setting of a collision preset, collision enabled. In our real engine, we have two types of collisions based on where they emerged from. Collisions emerging from physics, like an actor simulating physics and moving by some force, which we represent with the red ball, and collisions emerging from a query, for example, a projectile moving using its projectile movement component, which we represent with a blue ball. The collision-enabled flag allows us to decide whether a body instance will be involved in collision and what type of collision it will be involved in. No collision is clear, and will discard this body from getting involved in any collision checks, which can be a big performance win for background meshes that don't need to be involved in collision at all. Query only means that this body will not be involved in physics collisions. It will let a physics simulating actor, like our red ball, penetrate it or pass through it, but it can block our non-physically simulated blue ball. Physics only means the opposite. This body will only be involved in physics collisions. It can't block our blue ball, but it can block the red one and even get pushed by it if it simulates physics. Query and physics means that the body will be involved in both types of collisions. Probe only means that the body will not block physically simulated objects, but will still generate hit and overlap events when colliding with them, if both this body and the other object have generate overlap events and generate hit events enabled. Probe and query means that the body will have the characteristics of both query only and probe only. So, back to our example. Our projectile is not simulating physics because it's moving by its projectile movement component. So, for our wall to collide with it, it should be using any collision-enabled flag that has query on it. To ensure our projectile and wall are using the right collision enabled at the moment of intersection, we can go to the Show menu in Case Visual Debugger and filter Geometry Visibility flags to show objects with query collision enabled. And we can see that both our wall and projectile are visible at the moment of intersection, which means that they are using the right collision enabled setting. So, collision enabled wasn't the issue either. Let's move on to the third question. Does both objects have the right response to each other? The next important thing to look into in a body instance is its collision type, or to be more precise, its object type. Each body instance has an object type that it uses to determine how it should respond to collisions with other object types. Besides object types, there is also trace types, and the distinction between them is simple. Object types can be assigned to objects, and trace types can be assigned to traces. Think of a trace as a physical object, and it might make sense for you. What matters in the end is that they are all collision types or channels. And the engine allows us to create our custom types, but more on that later. Each body instance can specify one of three responses to use when it collides with another body or trace that has some collision type, including bodies of its same type. These responses are to ignore, overlap, or block. And when two objects have different responses to each other, priority is given to the least blocking response. If we think of them as numbers, where ignore is 0, overlap is 1, and block is 2, then to decide the result between any pair of those, we take the minimum number. This is known as collision filtering, and is probably the most important concept we need to be aware of. We can also think about it as two people passing by each other. If one stops the other to start a conversation, but the other totally ignores them or notices them but still continues on its way, no conversation will happen. Only if both of them are interested in talking to each other that they will stop and have a conversation. So, back to our question. Does both our wall and projectile have the right collision response to each other? First, we know that the right or desired response is for them to block each other. So, both of them need to block each other's collision type for that to happen. If we look at their details to figure out their collision types, we can see that the collision type of our projectile's collision component is wall dynamic, and our wall's collision type is default, which means it's defaulting to its static mesh's collision type, in this case, wall static. Lastly, we need to look at the response each one has for the other. We can see that the wall is blocking wall dynamic, the projectile's collision type, and the projectile's collision component is blocking wall static, the wall's collision type. So, we answered the third question. Both objects have the right response to each other, yet our issue still persists. But before we move on to the last question, we can see this process of figuring out the result of collision filtering can still be a little confusing and have some back and forth between objects. So, let's take a little pause and see a couple of ways we can improve this process. One thing we could do is to create a console command or a tool that determines the response of two objects and returns it to us. Here I created an editor utility widget that would take two components and return their collision response to each other. But these are patches for the issue. We didn't fix the root cause, which is custom profiles. If you think about it, this process could have been figured easily if we didn't have custom profiles. But custom profiles take away this advantage of grouping collision settings in a named preset. It makes the object unknown and confusing. So, let's see a couple of ways we can use to protect ourselves from falling into this bad practice in the future. The first thing we can do is to find any existing use of custom profiles and eliminate it. And there's a couple of ways we can do that. One very cool tool George showed in his talk is the ability to show references of custom profiles in the reference viewer. I was interested in integrating that in my project that I spent more than a week exploring how the reference viewer and the asset registry worked. I thought that I should create a separate reference viewer, as I saw that happen in the plugin reference viewer plugin. And after a messy time and a couple of trials and errors, it worked. But it didn't look good for me. So, I messaged George, and he was kind to let me know that it can be simply done in 2 lines by overriding the post-serialize function of the body instance and calling the mark searchable name function, which is similar to how gameplay tags are part of the reference viewer as well. But that required changing some engine code. So then I came across property coloration view mod from this talk by Chris Murphy. A nice view mod that allows us to control click on any property of an actor and view actors that have this property with the same value. But unfortunately, it doesn't work with custom profiles by default since they have a customized details view, but it can be added with this single line. Still, since this is an engine change and we can't always modify engine code, I guess my collision reference viewer plugin can still be useful somehow. Another command that came across my eye is collision.list components with response to profile, which lists components that have the specified response to the specified profile. So, I looked at how it works and created a modified version of it that simply lists components with custom profiles or a specific profile in the output log. So, there is a lot of different ways to find and remove existing use of custom profiles. The next thing we can do is to disallow or protect against any future use of custom profiles. And we can do that by either creating an asset validator that would check the collision profile of assets that could have a body instance like meshes and blueprints and warn us if it finds any asset using custom profiles. Or if we can modify engine code, we can totally eliminate the option from showing as George explained in his talk, which we can do by modifying the details view of body instance to remove this option. Now the question becomes, what do I do when I need custom profiles? The answer is simple. Create a new collision preset and name it after what it represents, not the response it will have. Also consider creating a new collision channel. If what you are modifying represents a physical object, like a projectile or a weapon, create an object channel. And if it's not a physical object, but a query, for example, a bullet trace that doesn't spawn an actual bullet actor, then create a trace channel and name it bullet or something similar. George also recommends documenting the list of presets to keep it clear and trackable what each one represents and should be used for. So, that was a long pause. Let's get back to our example and answer the fourth and last question. Is our query set up correctly? For our projectile and wall to collide, or for any two objects to collide, there must be a collision query behind that collision. What we mean by collision query is any function used to detect collisions. In our real engine, collision queries are used everywhere, sometimes implicitly by the engine. For example, for a character to stand, it performs downward line traces every frame to find the floor to stand on. For a spring arm to block camera clipping, it performs sphere sweeps every frame. When we click on an actor in the editor viewport, a query is performed to find the actor under the mouse cursor. And other times, queries are performed explicitly by us. For example, when we use a line trace by channel to shoot a bullet, or a sphere overlap actors to find closest actor to interact with, or when we set an actor's location and check the sweep option, we perform a sweep query. And in our case, our projectile is implicitly performing queries during movement updates by its projectile movement component. But to understand if our query is set up correctly or not, we must first understand what is a query made of and how it works under the hood. Like many things in Unreal, there is no one way to do something, and in the case of collision queries, there are many ways to perform a collision query. This flexibility sometimes can lead to confusion, yet it's a big advantage, especially with something like collision that often needs full control and customized filtering by us. So, it's our responsibility to understand the queries that we are using and the differences between them. And it's really not confusing as it seems. Every collision query has a couple of parameters: the type of the query, a trace, a sweep, or an overlap, the shape of the query, for example, a line, a sphere, or a capsule, the mode of the query, single, multi, or test, the collision filter of the query, which represents what collision types can be detected by the query, and then there's additional parameters of the query, for example, what actors to ignore, should it look for complex or simple geometry, and more. So let's break down each one of those. The type of the query: trace, sweep, or overlap. Traces and sweeps are very similar. They both cast a shape in some path that has a start and an end, and check what objects would collide with that shape if it moves along that path. But traces differ from sweeps in that they don't have a volume. That's why we only have a line trace, because lines don't have a volume. Unlike sweeps, which allows us to specify a shape with a volume, like a sphere or a capsule or a box. That's why in hit result we have a location and impact point. For a line, they would represent the same thing, but for a shape with a volume, the location represents the shape's location at the time of the hit, and the impact point represents the actual location where the hit occurred. An overlap, on the other hand, doesn't move along a path. It doesn't have an end location. Instead, it allows us to specify a shape at some location and find what objects are already intersecting or overlapping with it. Both sweeps and overlaps are used by movement components to check hits or overlaps during movement. If a sweep is performed during movement and it hits something, then the on-hit event for this component and the component it hits and for their owning actors gets called. If an overlap is found against another component, then whether this overlapping component started overlapping or ended overlapping, the begin overlap or end overlap event gets called for both components and their owning actors, if they both have generate overlap events enabled. Then there is the shape of the query. And shapes can either be a line, a sphere, a capsule, a box, or a primitive component, which, as we discussed in collision geometry, is made of simple collision primitives or complex triangles. The type of the shape and its volume impacts the cost of the query. But we will talk about that later on when we discuss collision performance in the next part. Then we have mode of the query. And mode can be thought of as what is the target of the query and what info do we need to get from it. If we need to just know whether we hit something or not, we can use test. If we also need to know what did we hit and the hit info, we can use single. And if we need to know all the objects that we hit and each hit info, we can use multi. These three modes perform the query against actors in the world, but it can be that sometimes we have a specific target we need to query against. So, a less common query mode is to perform a query locally on a specific actor or a component. For example, if we have multiple enemies trying to shoot the player, instead of each one performing a line trace against the world, they can perform it against the player, or even a specific component or body instance of the player, like its hand or head, for example. Then we have collision filter, or the functions that we are more familiar with, by channel, by profile, and by object type. I want you to think of these as who gets to decide the result of the query. Is it up to the object, or up to the query, or to both of them? If we think of a collision query as any physical object that has a collision type and a list of responses to other collision types, then when we use a collision query by channel, under the hood we set the query's collision type to the chosen channel and set its list of responses to all collision types to block. This leaves the object to decide the result, since the query already blocks every type. If the object blocks the query's type, then the result would be a block. When we use a query by profile, we fill the query's collision type and list of responses from that chosen profile. That leaves both the query and the object to decide. Both of them need to block each other's collision type for a hit to occur. And when we use a query by object type, we leave it to the query to decide the result. Because under the hood, we forget about the query's collision type and its responses, and instead we check only if the object's collision type is one of the collision types the query is looking for. Usually, we wouldn't care about these implementation details, but it matters to know that we have the ability to fully customize queries as we wish in C++. And it matters more to understand how they work under the hood, to use them correctly and avoid any misunderstanding. For example, one caveat worth mentioning is that if you ever used multitraces by channel, you'll find them working differently than multitraces by object type. Multitraces by channel or profile return at the first blocking hit, but multitraces by object type detect all blocking hits and don't stop at the first one. This happens because when we use multitraces by object type, the engine fakes blocks as overlaps, but it doesn't do the same when we use multitraces by channel or profile. Now let's quickly look at some additional query parameters that could be useful to know about. UseComplex is a flag we are familiar with that allows us to specify what collision geometry type to query for. Mobility type allows us to choose whether to look for static or movable objects only, or objects with any mobility. Then we have actors to ignore and also components to ignore. And we can also give tags or names to queries, which can be useful for debugging purposes if we combine that with the command trace tag, passing it a specific query tag to debug. For example, if we had a large project with multiple queries, we can decide what queries to enable debug drawing for with this command and without writing a single line. And there are more parameters that I won't get into much detail about here. Most of these parameters are not available in blueprints, so it's highly recommended that we create some wrappers in C++ that export them to blueprints. And a great way to understand these parameters by yourself is to get the query test actor tool George provided in his talk and play with these parameters to see their impact. Now we know how queries work. Let's get back to our example and see what query are we using. The best way to identify that than checking our projectile code is to use Chaos Visual Debugger. From it we can see every query recorded and see its full details, like its parameters and hit results. If we move our timeline to the moment of intersection, we can see our target query's details. If we take a closer look, we can see the queries emerging from our projectile's mesh, not from its collision component as I assumed. That's because if we look at our projectile class, we can see its mesh is the root component. So the projectile movement component uses it for collision queries by default. And we can see that it ignores world static, the wall's collision type. So we found our issue. And to fix it, we can set the mesh's response to world static to block, or tell the projectile movement component to query using the collision component instead of the mesh component. Now, trying to reproduce the issue once again, we can confirm it's fixed after we set up our movement component correctly. So, this was a long process, but before we do a recap of our findings, an extra edge case worth mentioning is that if our projectile was very small and fast, and we checked everything, but it's still not colliding with some objects, In that case, we should look at continuous collision detection and see the issue of tunneling. So, time for a quick recap of what can cause collision to not work properly and get out of control. For any non-physically simulated collision to occur, it must emerge from a collision query. Collision query has a shape and a collision type, like any physical object. For an object to be detected by a query, it must meet three conditions. It must have collision geometry that intersects with the shape of the query. It must have a collision-enabled setting that includes queries. And its collision type must produce an overlap or a block response with the query's collision filter. To keep collision manageable, we should avoid custom profiles and replace them with named presets. And to quickly detect collision issues, the best thing we could do, rather than asking these questions or assuming anything, is to record the session using Case Visual Debugger and look for issues at the moment of intersection. That wraps up part 1 of this 2-part video. I hope you get a better understanding of what can cause collision to not work properly and get out of control, and we can work with it easily in our future projects. In the next part, we focus on optimization and answer the question of what can cause collision to work poorly and cause performance issues. This was Amr. Thank you for making it to the end of this part, and I shall see you in the next one.